Maru,
Hello.
I'm here. Can you start now?
Okay. So continuing from uh, a data schema. So a data schema simply is a visual representation. In this case, it is a visual representation of the data model. So it simply has to do with what does our data model look like. That is what we refer to as a data schema. So I used to understand that even when a data model, in as much as a data model has to do with the relationship between tables, even a single table already is a data model. And generally in Excel, you mostly work with a single table. And as simple as that single table is, it is a data model. I treat over this a lot of times because a couple of people uh, tend to mistaken the fact that a standalone table cannot be a data model. It is a data model, and sometimes, in fact, in certain scenarios, a single table can even be your best shot at having a solid data model. But it comes with its own downsides and really heavy limitations, especially in Excel. So let's look at that. So number one, we have the number of rows. So in Excel, you have to have less than a million rows, which is not quite comfy when you're handling really large data. And when you get to having 1 million rows, I, for one, would not even advise still sticking with a single table model. So now would also have speed and memory usage. So for speed and memory usage, because you are traversing a whole lot of data to get out a particular piece of information from your data, the amount of data that gets loaded into memory is a lot, and the speed at which it goes through that data is relatively slower. In fact, sometimes visibly slower. And most times with your single tables, you can just perform basic calculations rather than writing really nice queries for your data. And the limit on this size now ends up becoming a major limit on the data model itself. So the size limit now extends out to become a major limit on the data model. So we would be looking at one piece of data that has such. Oh, let me share my screen. Okay. Okay. I hope we can see my Power BI desktop. Please kindly confirm, Miriam, is my screen up?
I can see it, but it's coming on and off. Why is that?
Uh, I don't know. Let me redo that.
Yes, it's stable now.
Okay, thank you. So we'll be working with a particular piece of data that's available in the Power BI results file. that we have a link to, and it's called single table. I think that's the name. So let me get data Excel single table in Excel. I open there. So I always do preview before I bring in any data. Mm. So I just bring in the two. Wait, that's still getting in. Okay. So we have it in. So let's just take a good look at the data. So for this data, I just need us to look at this. It cuts across a couple of different things. So I'd have loved to merge this first of all. Data looks like they are mirroring. Look at sheet one again. So both data actually are mirroring each other. So this is just for basic explanation purposes. So now let's start picking out key concepts that relate to data modeling. Hi, Miriam, can you still hear me? Just please confirm.
Yes, I can hear you and I can see what you're doing.
Okay. So we'd first of all talk about granularity. So granularity is simply the level of detail of your table. So we've been working with a particular piece of data for a while, so I expect that we'll be a little familiar with it. In the practice data, we can see that under product category, after product subcategory, we also had product name. So that was more specific, that had higher granularity. So in a case where we have more columns, so now I'm talking about the relationship between granularity and the number of columns. The more the columns, generally, the higher the granularity. So more columns generally means higher granularity, because if you're having more columns, that means you're having more specifics. So as in the case of practice data where we had uh, in the product table, we had product name, we even had product description. So the granularity of that data was really, really high. So higher granularity simply interprets as uh, more detailed information, which also in most cases means you have a more powerful model and also an increase in the number of rows. I hope you understand that. Because higher granularity means you have more details, and having more details means your data is larger and more specific. Meaning, when you are drawing out inference, your inferences are more powerful because they are driven towards specifics. So that is one thing that should be aimed at when you're running your analysis, that your inference is being drawn towards specifics. That way your your analysis can be even a slight increase in your analytical prowess, or a slight increase in the accuracy of your analysis can yield more results. So we'll be looking at the lower granularity, on the other hand, has to do with a faster and a smaller model, like what we have here. So this is generally smaller and it's going to be way faster to traverse, and also has less analytical power, because by the time we are predicting, say that the pricing for air conditioners is, or the sales amount that the sales we've made for air conditioners, we cannot predict what particular product is doing well. We can only tell you that it's an air conditioner. So what if you're investing into the air conditioners and investing into the wrong part of the business and all of that? So try as much as possible to increase the granularity of your model, especially when you are going to go as far as, in fact, even from your historical analysis, you should, or your descriptive analysis, you should try your best to have a standard data model. So now, granularity and table size. Increasing the granularity increases the size of the model. So as I said, you have more columns, which you would, one way or the other, interpret as you having more rows. Because if you have more columns, that if you have more specifics, that means there'll be more populations for those columns based on what has been broken down from air conditioners to very specific products. So you also have more rows, meaning you will also quickly hit the 1 million rows limit that Excel has. Because let me use a practical example. So say you have a category, let's say home appliances. So let's use this here. Okay. So I'll just scroll a little so we could find another category other than home appliances. So we can see the way home appliances is broken down into, you have lots of home appliances here. So I'm sure almost till the end we'll be having lots and lots of home appliances. This is not a query editor where I can just quickly get out what I want. And we have cell phones. So let's say if we can still reduce the granularity of this by breaking it down into just home appliances and cell phones. So where what has covered over uh, so now we have 8 distinctive values on that product category name. Now by the time it's broken down into product subcategory, we now have 32 distinctive values. So if we want to make this smaller, we could just do away with the product subcategory and group everything back into their categories, and you can tell out the sale quantity of each category. So that means we have less column and also less rows, because instead of that, will now be, instead of having it repeated over time, we can now have probably 32 or 8 rows if we like. So we can reduce the granularity of this. But when we're now making our analysis, we would now see that our analysis would not even be close to accurate because it is too generic. Okay, we say cell phones made, let's say, 1 million in profit. What particular phone brought in that profit? What particular phone grossed that profit? So sometimes a particular product might be more successful than other products, but the product category might not be as successful as others. And if you are saying, okay, invest in so line because it is doing well, you might also end up not investing in a particular product that is even doing better than the entirety of another product line or another product category, which is why our granularity should always be checked dependent on the scenario in which you use such uh, a model. So we should always check for that. Now we'll now talk about having scattered information. So the higher the granularity is not always, as I said earlier, the best choice, because having too high a granularity that is too high, that is really high, is as bad as having a granularity that is too low. Is as, in fact, is as bad, if not, because remember, we're also talking about speed and memory usage here. So having a table that has really high granularity is as bad as having a table with really low granularity. So now we'll talk about leveraging a data model, and let's first of all look at the data model. So we'll see what we're saying here. But we can see that they are standalones as against our other data. So now I would be bringing in the other data that we normally work with, just practice. So I'll just bring in the necessary tables and leave out the rest. So mm, and load this in. Okay, that is loaded in. Now we would also look at the data model for this other one. So now This will bring us to another key concept called relationships. So let me close these properties so we could see this more clearly and close fields. So now it will bring us to the key things called relationships. And simply, a relationship defines how data sources are connected with each other. And you can create interesting visualizations on multiple data sources based on these relationships. So in this type of image here, you can see a really common data model, and we can see the relationship between the customer table and the sales table. So, and what is joining them together is customer key. Now, we'll now look at different kinds of relationships. Let us listen closely. For relationships, we have one to many, we have one to one, we have many to one, and we have many to many. The direction of the arrow determines what way the relationship flows. So now here we have a one to many. Many is represented by an asterisk here, and it flows one to many. So usually it flows from dimension to fact, which brings us to explain the differences between facts and dimension tables. Before we do that, we have to understand what makes them the way they are. So, and what does that is business entities. Earlier, I was saying how in data modeling or your schema, it has to be in line with how it relates to real world entities, or in this case, as we'll call it, business entities. Now, every business entity deserves a table. So each business has different entities, and by entities I mean parts or categories or distinctive features. So in this case, we have features like product, customers, sales, uh, uh, dates. In case of medical data, we'll be having patients, medications, doctors, and so on and so forth. In For engineers, we'll be having teams, we have workers, we have buildings, we have projects, we have frameworks, and so on and so forth. And for techies, we'll be having software, we have features, we have bugs, we have customers, we have for software, we have frameworks, we have language, and so on and so forth. So each business has its own unique entities or has different entities under them. So take the business or the model set. Set that has other sets within it is where these two sets, which belong to this entire universal set. So our data model is taken as a universal set, and we have two subsets under where, and there is a place where those sets overlap, as we have in a Venn diagram. So rather than having a Venn diagram, here we have the relationship being shown. Okay, so as I was saying, each business entity has its own unique characteristics. And by that, we have customer being a business entity, And under the customer entity, we have address, line, birth date, common distance, and so on and so forth, education, gender. For territories, we have country, group, region, sales territory key. For sales, okay, let's look at the other one for product. For products, we have category, color, dates, manufacturer, and so on and so forth. Then for sales, we now have customer key, order date, sales territory key, ship date, total product cost, unit price, and so on and so forth. So as we take a note, every table, or in fact many, not all, so I don't generalize, many tables, many tables need a relationship. Not all, but many tables need a relationship. And oftentimes that relationship is that relationship is shown here the way it is by an arrow. So and every relationship links two tables. Every relationship has a direction. In this case, the customer has a one side and the sales has a many side because there are many sales to one customer. Do you understand? So there are many sales to one customer. We have many sales being made to a single customer. So it's a one too many. So one customer purchases numerous times. So the best practice states that you should use the same column name for your relationship on both sides. Use the same column name so it can easily be identified by Power BI. So sometimes when you use different column names, you would not have to come here, manage relationships, and you can either use auto detect, edit, or new to create a new relationship. So let me just drop the relationship between our sales and product key so that we can on customer key so we can see. Let me delete this. See that it warned me, let them create a new relationship. So I'll be having a customer. I'll be picking the customer key. It's really easy to use. And I'll come here, pick sales, and pick the customer key also. So most times, especially when you're creating, you'll be the one to select the relationship and how it relates. I hope you understand this. We don't want to create this relationship and decide how it relates and check the cross filter direction. So by cross filter direction, we mean this the way it moves. So now it doesn't move in both ways or just one way. So now we'll just click OK to get a relationship. And generally, it is advised not to use a many to many because it breaks. So we can see, I hope, okay, this relationship has cardinality management issue. Only be used if expected that neither column contains unique values. That is so we'll stick to one to many so that we could just see that many to many most times breaks our model, not all the time. So I'll activate these relationships back and Oh, sorry guys. So I have to change the direction of this. So, okay, let me close first so that we can see. Okay, let me. Understand that it's a one to many, so it's automatically just put it right. I hope we get that. Um, Now we've talked about relationship. We've talked about business entities. So uh, let's continue. So now we're talking about granularity earlier. So we've looked at how granularity looks like in a single table, but with multiple tables, such as in our practice data, granularity with multiple tables is an entirely different ball game because each table has its own granularity. So we have customers at the customer level, dates at the date level, product at the product level. And in this case, sales has its granularity defined by the related tables, which is why we'll be talking about facts and dimensions. We'll see that in a while now. So it has its granularity defined by the customer date and product level. So if you have uh, those three tables attached to the sales data, that is basically how it would look like. So its granularity is not necessarily defined by itself. Now, which will bring us to normalization and denormalization of data. So this is another important concept that we have to understand. So normalization, firstly, is the process of organizing the columns or the attributes of a business entity and the tables of our data to reduce data redundancy and improve data integrity. So by data redundancy, what do we mean by data redundancy? So if we're talking about data redundancy, it has to do with uh, the storing of same data in multiple locations. So having repetitions of the same data, that's what we mean by data redundancy. As we saw with the other model when we're talking about working with single tables, we're talking about data redundancy there. We're looking at a redundant data that occurs numerous times in memory. So we reduce that by normalizing the data, which also increases the which also increases the 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 what's now reduces rather the level of granularity, so we don't have it repeated numerous times. So imagine we the same way to ease in the sales table, where for each purchase we recorded it like that also in the customer table and in the product table. So we would be having issues with that. So we just split each business entity individually so it doesn't have to repeat itself so much across board. So that process of organizing the columns and tables is called normalization. So denormalization is actually the opposite, increasing the data redundancy. Sorry, increasing the data redundancy and having in mind that the reason why you are increasing the data redundancy is to improve the understanding of the model. So sometimes we can still further reduce how redundant this data is by So in the case of normalization, most times normalizing your data involves reducing the granularity of that data. Most times, not all the time, but in most use cases, normalizing your data will involve you reducing the granularity of that data. And sometimes, how far you reduce the granularity can mess up your entire work. Sometimes, not all the time. Remember, in data analysis, it is your use case. So, your own case. And this time, we're talking about sales data. So, in this case, granularity levels would surely drop when we decide to normalize. Because if we want to normalize this data, we would compress all the categories. So we'll no longer be having product key as a relationship. We're having product categories. So compressing the data to reduce data redundancy. So when we're working with a single table, so if this entire data was on a single table, the whole columns, all columns will be denormalized. Because if all this, if the entire data here was on a single table, we would be having it repeating itself a lot of times. Because in the case of an entity like customer key, sometimes a single customer might buy a particular product like 5 times. So if it's in a single table, that customer key would appear 5 times. So it will appear multiple times like that, on and on and on and on. So that means the address will now appear multiple times. That means the gender will appear multiple times. The last name, so things like that. So we'll now be having a really bulky model. So if you're having a single table, when you're working with a single table, keep it in mind in a single table, in fact, except in the in a case where you have a data modeler already normalize that data. Actually, single tables are fully denormalized in that they will have multiple values. So when we talked about okay, let me make it very particular. Single tables with good levels of granularity are denormalized. A single table with enough granularity for you to work with is almost 90% of the time going to be denormalized. So if you look at your data, you would see it that it is denormalized. While normalized models usually has to do with having it in this form. This form is normalized, although not fully normalized, because as we know, too high is as bad as too low. So your this table is just normalized. It is not fully normalized because we can still normalize it further. So we'll now be looking at a denormalized model. So denormalization is actually welcome to make the model easier. So sometimes you might just need to split up things a little to just make it more understandable. So as in the case with this, this model here that we have is, as I said earlier, not fully normalized. So we still have some certain levels of denormalization where we have all this broken down: address line, the date, full name, gender. So in a normalized model, you will have just the customer key, because we don't want to do with a fully normalized model. We won't want to deal with all of this. So we just have really important ones here. And sometimes to make our analysis, so we might be needing a couple of these other factors to put them into place. So remember, a denormalized model makes it easier to understand. So it's advised, do not use a fully normalized model. So now we've talked about schemas at the beginning. So now let's take a look at our data and describe the schema that we see here. It's called a star schema. So basically, there are two schemas that we'll be coming across and using a couple of times throughout our career in data analysis, and they are the star schema and the snowflake schema. So to start with, let's start with the star schema, which is what we have here, and even the more simple of the two. So the star schema usually has one fact table, usually, emphasis on usually has one fact table and other dimension tables. So as I promised, as I said earlier, we'll talk about facts and dimensions. So different entities are handled in different ways or have different ways of handling. And for this, we need to understand that there are two ways that this data appears. It either appears, if these entities appear rather, it either appears as something that has happened, or it appears as something that describes what happened. So I'll come here. Business entities would always appear in two forms. Either appears as something that has happened, or something that happened, or something that describes what happened. So for something that has happened, in this case, we have sales. Another example is cash withdrawal at an ATM. Another example is prescription of a medical treatment, or a doctor prescribing or attending to a patient. That is what happened. Now, business entities that are in the form of what has happened or something that has happened are called facts. So sales is something that has happened. A sale has been made. Now, dimensions, on the other hand, describe the fact. So dimensions describe the fact in that they work like this. Okay, a sale has been made. What describes that sale is what was sold, who it was sold to, where it was sold, and basically, in the case of this data, that's it. What was sold, which is product. So we have sales being the fact table here, right? Then now we have product describing what was sold. Product key will describe what was sold. Customer key will describe who it was sold to. Territory key will describe where it was sold. So now, so we can get this clear. Using of keys helps to normalize your model. So in the sales table, you do not have all of this listed out. You just have a key, which is usually numeric here, that relates to this. And now, I would love us to understand something about facts and dimensions. Usually, fact tables contain numeric data. Take note, fact tables usually contain numeric data. Emphasis on usually. Now, I would love us to understand something about data modeling and even data visualization. Data modeling and data visualization are usually based off best practice and use case scenario. Best practice is what I'm explaining now, which is why I keep saying usually. I keep saying usually because that is what should actually be done. But there are always going to be exceptions when you work, which is where comes your creativity to be able to do add 2 plus 2 together and just tweak it. So generally, or as I would say, as I said earlier, fact tables are usually numeric in nature because, for example, the sales, cash withdrawal, the prescription, they are usually numeric in nature, and the descriptions are usually categorical or non-numeric in nature. So that doesn't mean that there can't be a switch over or something, which is I would understand that one business entity makes one table, and all attributes of that entity reside in that table. So attributes of a fact reside in the dimensions. Now, in the dimensions, each entity is in its own table, and attributes of that entity reside in that table. But the attributes of your fact table resides in the dimensions. Attributes of the table reside in the dimensions. So take note that usually country is not an entity. Usually countries is not an entity. Usually countries is not an entity, it is an attribute of other dimensions. Because okay, let's look at it here. Where we have in the customer table, we have location. Sorry, we have address. Now, this address usually is something like country. So country also resides here in territories. So usually it is not an entity, except in cases of demographic data, where we have something like population. And in that case, population would be a fact table. So the dimension country would be, which is an entity in this model, territories. So it contains a kind of demographic data. So it is just in case of demographics where we have population being a fact table and dimension referring to country. So now, when the tables, remember a schema is more like a cognitive or visual representation of your data model, how your data model looks. So when you're placing your tables, for this is now is best practice or general use for creating the tables. The fact table stands alone in the center. So as we have it with the sales, stands alone in the center. Let me give him some. Give. Let me declare. Stands alone in the center. That is how the fact table is. It's alone, connected by all of this. And the dimension tables are around the fact table and are directly linked to it by this. Remember, it's directly linked to it. And the figure that appears looks like a star, with hence the name, the star schema. So if we add more related data and it's all around it, you would notice that it looks like, even now, it's just that it's not fully, it's not really complete. It still looks a little like a star. So hence the name, the star schema. So let's understand the importance of a star schema. So generally, a star schema is very easy to understand. So once you look at a star schema, as long as you're familiar with it, you understand. As long as you're familiar, even for those that are not really familiar, when you look at it at first glance, it is relatively easier to understand the relationships and the way your data, the profile of your data by looking at a star schema, other than looking at it in a single table. So we can't really tell how this data. So let's go back to the other data, except we've deleted it. This data we can't tell. We can really, although it's really small, but we can't tell how each of these relates to each other here as it stands. But when we come to our other data here, just simply by looking at product, sales, territories, customer, we can tell that, okay, there is one product here in product that has been sold many times just by looking at it. So it makes it really easy to understand at first glance. And you can slice out you can slice out by dimensions and aggregate your facts. So what I mean by that is when you this is for Tomide was always asking about functions. So you can slice out by dimensions. So you can take a particular dimension, let's say product line or product color, as we did with group by, and slice out to get your sum of your facts. So you can. So Tomide, I hope that that should answer your question about functions a little. So there are easier ways to do it using group by, and rather than always depending on using visualizations and so on and so forth. So we talked about slicing by dimensions, and here there is no ambiguity. It's not so clustered and so bogus. It's easy to see through, and the level of direction makes it easy to see the rows of the tables. So there's just one level of direction. So it makes it really easy to see the role of the tables. And it is very fast. A star schema is, in fact, we can say it is generally accepted as the standard schema for data analysis. Because most times, modern engines and TPUs, CPUs, GPUs are optimized to work with star schemas. Remember, your data is always going to be stored somewhere, and there's always going to be a processor processing it. So most times they're already optimized to work with star schemas, which is why because it is, in fact, the most common schema on ground. So it helps us drive a clean modeling path. So to drive a clean modeling path, so that we can just understand what I mean by that, I mean general practice. How should a star schema look? So in a star schema, usually, as I said earlier, the numbers should go in the fact table and the strings should go in the dimension table. Then for every other thing that doesn't directly fit into our numbers or strings or numeric or non-numeric, we just have to understand where they need to be. So this is for a cheat. That's what I like to call it. It's just a bypass. So rather than so you don't think too much, you just organize it and put all your numeric data into the fact table as we have here. All the numeric data is here. So if you look through this, you will see any data that is non-numeric in sales. But you can see the non-numeric data here in customer. You can see non-numeric data here in territories. You can see non-numeric data here in product. So that's just a cheat way to just get your data modeling done really quickly, especially when you have our particular table. So you just move the columns into a new table. So that's how to create a new data model. So to create a data model or to normalize or denormalize the data as we have come to understand it, we know that you just simply move the data in to where it's supposed to be. So let me use this so we could see more. So we can see this looks more like a star, although it's not complete. So it's just basically how the star schema works. Okay. So most of the time, if you don't have a star schema, you're actually in trouble. Not all the time, most of the times, because any changes made in your model to make it look more like a star schema is a right step in the right direction. It is a really good step because as we can see through the examples we've looked at, your model is not really different from any other person's own because basically it just has to do with how it relates to you, but in its entirety, it is not really very different. But as anybody else, we all have special models or the way no two models look exactly alike because the way I would factor out and bring out the dimensions and facts might not be the same way you would. So everybody's models are different. But however, a star schema would fit almost any model that you decide to bring. Because once you identify where the facts, what are the dimensions, boom, there you have it. You know where and how to organize your star schema, which will now bring us to the snowflake schema. So now, looking at a snowflake schema is designed really easily by bringing out data that is underneath here. So your dimensions. So remember when I was talking about having just one level of direction? When I was talking about star schemas, snowflake schemas has multiple levels of direction. So the way your sales table carries the descriptions. So now everything that describes the customer would now be put in another group of tables. So it's now saying your dimension subset has its own subset. So now you have dimensions defining dimensions that define facts. So that's basically how the snowflake schema works. So in a snowflake schema, you can have your data fully normalized because each of those tables, but you'll be having a lot of tables, but each of those tables can be fully normalized. Although most times we never ever fully normalize data in data analysis because of the reasons I have already stated earlier. So that's just how it works here in for data modeling. So now that we understand data modeling, so let's just look at the jobs that have to do with data modeling. So data modeling means that you should understand the pattern of the data that you are working with. So that means you should have a domain expert that actually understands how the data relates and how they work. Because certain times, especially in cases like medical data, your facts and your dimensions are not that clearly stated. But someone that is a medical practitioner can easily understand that. So you should be able to know that. Then, because of that, you should match your model. The next thing you do as a data modeler, after understanding the pattern, is you match your model to the pattern. So you just match your model to the pattern that is already on ground. After applying the pattern, you notice the small differences that appears to make your model really unique. Then also, these patterns are learned with experience because the more you work on a particular kind of data, the more you get to understand. So the goal is not just to learn those patterns, but actually see them in action. So as I said at the beginning of this, when you start, you always feel that your model is really different from the regular models. But you need to understand that it's most time, in fact, 99.9% of the time, that is not the case. Because most times it's not really nice to deviate from standard modeling unless you are really, really sure that your pattern does not fit the model. And business intelligence has been existing for over 60 years. And this is from people that have done business intelligence and data analysis for way longer than I have. And they've discovered that star schema still stands as the best option for this. So, for data modeling. Now, there, there are a couple of common scenarios that we can look at. So, we would be having cases where you have multiple fact tables. So in that case, what you can do to handle multiple fact tables is to normalize that data. So you normalize it and uh, and merge your data. So that's simply how to do it. So that is basically how it's done. So now we can look at that later on in our next class. So Miriam, hi Miriam, hi Miriam, hi, hi Miriam, hi, hi Miriam.
Hi.
So was it still recording?
Yes.
Okay, so I'm done. So you can end the recording.